Hi students, welcome to fourth lecture of microwave waveguides. In this fourth lecture, we are going to see the derivation of field equations for rectangular waveguides, or we can also call it propagation of waves in rectangular waveguides, or solution of wave equations in rectangular waveguide, or the analysis of field equations in rectangular waveguides. Okay, so all these mean same. In this, why actually we find out these wave equations? Okay, this is a common analysis which will be used for understanding about transverse magnetic mode of analysis as well as transverse electric mode of analysis. This is a common analysis which we will be finding before we proceed towards TE and TM mode of analysis. Okay, so first what we should do is we should try to take a rectangular waveguide which is shown and kept in the direction of Z. Okay, and that A is the broader wall dimension, okay, which is nothing but the breadth will be kept along X direction. Okay, breadth A is along X axis and width B is along Y axis, and the electromagnetic wave will be propagated in Z direction, which is shown. Okay, that waveguide will be towards us. If you assume your computer screen, okay, that Z direction, we should assume that waveguide will be present. Okay, now that means if you have taken the electromagnetic wave which is propagating in that waveguide in Z direction, and along x-axis we have the breadth or broader dimension A and width B along y-axis, and assume that the waveguide is filled with air as the dielectric. Now we'll be moving to the wave equations that we have already derived in EMF, okay, which are the wave equations in free space in terms of E and H, because these are the equations which we have to use even though the electromagnetic wave is assumed to be propagating along waveguide, but inside a waveguide it is filled with free space. We should assume that the wave equations in free space itself. But in free space, these wave equations are expressed in terms of E and H as del square E is equal to mu naught epsilon naught into dou square E by dou t square, which we call it equation number 1. And similarly, in terms of H, it is del square H is equal to mu naught epsilon naught into dou square H by dou t square. This is the second equation. Now, if you expand this E vector on both sides in equation number 1, and similarly if you expand H vector in equation number 2 on both sides, that E can be expressed as Ex Ax bar plus Ey Ay bar plus Ez Az bar on both sides, and comparing only the Z component terms. Why we are comparing only Z and writing it in terms of Ez and Hz? The reason is we are going to, in the next step we are going to find out the field components like Ex, Ey, Hx, Hy in terms of these Ez and Hz. By getting these equations only in terms of Ez and Hz, we need to find out the solution for this. Okay, for finding out the solution we need to apply boundary conditions. Once we get those solutions of Ez and Hz, we need to substitute these Ez and Hz in other field components Ex, Hx, Ey, Hy. That is what is the entire process that we are going to do in this complete analysis. Now, after comparing this Ez terms and Hz terms from the equations 1 and 2, what we will be getting is del square Ez is equal to mu naught epsilon naught into dou square Ez by dou t square, which we called it as equation number 3. And similarly, del square Hz is equal to mu naught epsilon naught into dou square Hz by dou t square, which we called it as equation number 4. Right? Now, I will be substituting the value of dou by dou t, which is equal to j omega, which everybody might have seen in EMF, and similarly the dou square by dou t square is equal to j omega whole square, which is nothing but minus omega square. So now replace both in third and fourth equations. Dou square by dou t square is equal to minus omega square. Now the equations 3 and 4 will become del square Ez is equal to mu naught epsilon naught will be as it is, and in place of dou square by dou t square we will be getting minus omega square, and Ez will be as it is. So the equation will now become del square Ez is equal to minus omega square mu naught epsilon naught into Ez, and similarly del square Hz is equal to minus omega square mu naught epsilon naught into Hz. And this equation we will be using it for transverse magnetic mode of analysis. I told you already, for transverse magnetic mode of analysis Hz will be 0 and Ez will not be 0. Ez which will be present here. Okay, that's the reason I'll be calling this particular equation is for TEM wave. Now this equation consisting of Hz, and that will be using it for the TE mode of analysis or TE wave, for which Ez will be 0. Okay, so we cannot use this equation for TE mode of analysis, and we cannot use this equation for TM mode of analysis. Okay, now what I'll be doing here is I'll be expanding this del square. We know that the expansion of del square is, in terms of rectangular coordinate system, is dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Okay, and Ez is also there. So dou square Ez by dou x square, which is here, and similarly dou square Ez by dou y square and dou square Ez by dou z square, which is equal to minus omega square mu naught epsilon naught into Ez. I call this is equation number 5. Similarly, we can also expand the other equation, which is in terms of Hz, that we will see next. But the most important part of this entire analysis here is we can even replace this, dou square by dou z square, okay, with some component. And what is that component? We'll try to see, okay, in the solution of Ez. Okay, Ez in time domain can be expanded as E naught into e power minus gamma z into e power j omega t. So here E naught represents the maximum amplitude of this Ez, and exponential of minus gamma z, where gamma is the propagation constant and z is the direction of propagation, which will be indicating that the amplitude is going to decay exponentially, and e power j omega t will be representing its varying with respective time. Now differentiating this Ez with respect to z, what you will be getting is dou Ez by dou z is equal to E naught into, differentiating this e power minus gamma z with respect to z, you will be getting e power minus gamma z into minus gamma and e power j omega t. Now writing minus gamma initially, first, and next E naught into e power minus gamma z into e power j omega t, and comparing it with the left hand side, then dou by dou z can be replaced with minus omega, right? And going to this next, and dou by dou z is equal to minus gamma, and the dou square by dou z square. That means if you differentiate again, what you will be getting is minus gamma into minus gamma, because that is a second derivative, which you will be getting as again minus gamma. So minus gamma into minus gamma will be gamma square. And similarly, if you differentiate thrice, that is dou cube by dou z cube will be minus gamma into minus gamma into minus gamma, which is minus gamma cube. Now in this expression, in the previous expression, what we have is only dou square by dou z square, which will be replacing it with gamma square. Now I'll be doing that. So dou square Ez by dou x square plus dou square Ez by dou y square, plus in place of dou square by dou z square, what we have is gamma square. I'll be writing that gamma square here, into Ez, which will be as it is equal to minus omega square mu naught epsilon naught into Ez. But this is an expression which is in terms of Ez, this is an expression which is in terms of Ez, so I'll be bringing that right hand part to the left hand side, then it will become plus, so that will become gamma square plus omega square mu naught epsilon naught into Ez is equal to 0. And that gamma square plus omega square mu naught epsilon naught, here everything is fixed here. Mu naught epsilon naught are the terms which are related to the velocity of light, and omega is also fixed mostly, and gamma square is also fixed. Okay, then the whole expression will be replaced with, and you will assume it as a constant, and that we are calling here as some h square. Okay, so you are going to now replace this entire expression gamma square plus omega square mu naught epsilon naught with h square, that will be finding out later, and substituting that h square in the sixth equation, what you will be getting is dou square Ez by dou x square plus dou square Ez by dou y square plus h square Ez is equal to 0. And this is the seventh equation which we'll be using for TM mode of analysis. Okay, we'll find out the solution of this Ez and we'll be using it in TM mode of analysis. And similarly, if you do the analysis for the equation, which is shown here, okay, this del square hz, if you expand it and if you substitute dou square by dou z square, which is equal to gamma square, and bringing the right hand term to the left hand side, and what you will be getting is this equation. Which is dou square hz by dou x square plus dou square hz by dou y square, and h square hz is equal to 0. I'll be using this for TE mode of analysis. Okay, and this equation will be used for TM mode of analysis, and this equation will be used for TE mode of analysis. So in both the cases, we will be finding out the solutions of Ez and Hz, okay, which are actually functions of x and y independently. If you observe this dou square Ez by dou x square, which is not becoming 0 individually, that means Ez here is a function of x, and similarly here Ez is a function of y. Both Ez are independent functions of x and y, as well as Hz is also independent functions of x and y. Okay, so we will take that and we'll try to find out the solutions for both of them, and by applying the boundary conditions we'll get the final solutions, and we'll be substituting these in the different field components, and those will be the equations which will be deciding what particular mode of propagation will be existing. Okay, so that's the end of this lecture. If you like my lecture, please subscribe my channel